In the last video, we introduced the concept of force and provided some basic idea of how forces work. In this video, we will introduce several different types of forces and use Newton's second law to relate them to acceleration. To keep things simple, the forces in this video will point either in the x direction or in the y direction. We will use a simple example of a rocket to illustrate the process of solving force puzzles. It's a little different from the process for kinematics puzzles. Consider this puzzle. A 200 kilogram rocket is initially standing still. Its thrusters will provide a force of 500 newtons. What acceleration results? The first step of this puzzle is our usual drawing of a picture, same as in kinematics. Here is our rocket. But the second step is different from kinematics. We don't need to take two photos. That's because in force puzzles, we're generally either solving for an unknown acceleration, as in this case, or an unknown force. Both are quantities that usually stay constant within a forces puzzle. Instead, we draw a second picture known as a free body diagram. This is a way of cataloging the forces that occur on an object. In a free body diagram, we represent the object as a spot and draw one arrow to represent each force vector. The size of the arrow is proportional to the strength of the force, and the direction of the arrow is the same as the direction of the force. We label each arrow with the type of force that's acting. In this generic case, where the rocket's thruster is applying the force, we call the force an applied force and label it F sub A. The third step is the same as before, setting the origin and axes. We always set the origin and axes on the free body diagram. We always set the origin on the spot. However, we can choose which way we want to be positive. In this case, we will set rightwards as positive. The fourth step is to find the total force in each direction. Here, there's only one force acting on the rocket, the applied force, and it's in the x direction. So we say the total force in the x direction is composed of just one force, the applied force. But now, look at Newton's second law. Total force equals mass times acceleration. So we can substitute the applied force in to get applied force equals mass times acceleration. Step 5 is to set the total force from step 4 equal to mass times acceleration. Step 6 is to substitute all the known information into the equation from step 5. Here, we know the applied force, 500 I hat newtons, the way we've drawn it, and the mass, 200 kilograms. Step 7 is to solve for the unknown. The acceleration is unknown, and we just need to divide both sides by 200 kilograms to solve for the acceleration. The acceleration is 2.5 I hat meters per second squared. This is the process for solving all force puzzles. It's similar but not identical to kinematics puzzles. The steps are: 1. Draw a picture. 2. Draw a free body diagram. 3. Set origin and axes. 4. Find the total force in the x direction and in the y direction separately. 5. Use Newton's second law to set total force in each direction equal to mass times acceleration in that direction. 6. Substitute for the knowns. And 7. Solve for the unknown. Some forces are seen very commonly and have their own symbols. Even more interesting, these forces can be calculated from other quantities. You don't have to be told their values directly. For instance, this 2 kilogram coconut is falling from a tree because it feels a force of gravity from the earth. For this coconut, or for any object close to the surface of the earth, the force of the earth would be calculated from Newton's second law. The force of gravity is also called weight. We will symbolize it with the capital W with a vector sign. We can calculate the value of weight using F equals ma. It would work out to 2 kilograms times acceleration due to gravity, which on Earth is 9.81 meters per second squared. The size or strength of the force then works out to 19.62 newtons. We always treat the sizes of vectors as positive, and will stick to that convention in forces. Since acceleration due to gravity is used so frequently, especially in forces, we give it its own special symbol, the lowercase letter g. So the equation for weight is commonly written like this. Weight is equal to mass times gravity. W equals mg. Now be careful of one thing. Weight and mass are not the same thing. Mass is a measure of the quantity of matter within an object. Weight is a measure of the gravitational force on it. So for example, if you were in intergalactic space, far away from any planets or stars, your mass would still be the same as what it was on Earth because the amount of stuff in you has not changed. But your weight would be 0. You would be feeling no gravitational forces at all. In the rocket puzzle, we knew a force and we solved for an acceleration. Now we will see a case where we know the acceleration and need to solve for a force. The weight force will help us in this puzzle. Consider this puzzle. What force does the ground exert on a stationary 2-kilogram coconut? Let's use our process. First, we draw a picture. Second, we draw a free body diagram. Gravity always pulls the coconut toward the center of the Earth. But if weight were the only force acting on the coconut, it would accelerate. It's clearly not accelerating, so there must be some other force to exactly balance out the weight and to make the acceleration 0. Whenever an object rests on a surface, it is experiencing a support force from that surface. This support force is called the normal force, and it is symbolized with the capital letter N. Unlike weight, the normal force does not have an equation. We have to deduce its size from other forces. But we can easily find its direction. It always points at right angles to the surface that the object is resting on. Here we can say the floor is pushing up on the coconut to prevent it from falling down to the center of the Earth. Third, set origin and axes. We will set upwards as positive y. Fourth, find the total force on the coconut. The total force is composed of 2 forces this time. The normal force pointed up and the weight pointed down. Because they are in opposite directions, we take the difference. We symbolize this as follows. Total force equals normal force minus weight, or total F equals N minus W. Fifth, apply Newton's second. We set the total force, N minus W, equal to mass times acceleration. Sixth, substitute for all knowns. The mass is 2 kilograms. The acceleration is 0 because the coconut was standing still. But we know something more. Weight is given by the formula mass times gravity. Again, we know the mass, 2 kilograms, and we know g, 9.81 meters per second squared. So we can solve for weight, 19.62 newtons. Then we take that value of 19.62 newtons and use that in the force balance. Notice that we don't need to explicitly say the weight is pointed in the negative direction. When we subtracted the weight in the original force balance, that took care of the negative sign for us. We now have normal force minus 19.62 equals 2 times 0. Simplifying both sides, we find the normal force equals 19.62 newtons as well. We have now solved a puzzle where 2 forces point in opposite directions and one was unknown. Here, we see two horses pulling on a cart. The horses are connected to the cart via ropes. Ropes introduce a new type of force called tension. Like the normal force and unlike weight, tension does not have a formula. The tension in the ropes are caused by the horses. This is what accelerates the cart from rest. Consider this puzzle. A 100-kilogram cart is drawn by two horses, each drawing its own rope. The acceleration of the cart is 1 meter per second squared rightwards, and the tensions in the two ropes are equal. Solve for the normal force on the cart and the tension in each rope. First, draw a picture. Second, draw the free body diagram. Weight points down, normal force points up, and the tension in each rope points rightward. I'll draw two tensions for two ropes and two horses. We'll call them T1 and T2. Third, set origin and axes. I will set rightwards as positive. Fourth, find the total force. This time we have forces in both x and y, so we have to solve these separately. For the sake of flow, I will completely solve things once in y and only then turn to x. The total force in y consists of two forces, normal pointing up minus weight pointing down. Step 5. We set the total force equal to mass times acceleration. Step 6. Substitute for all knowns. The normal force is unknown. But the cart isn't moving in the y direction. It is not falling towards the center of the Earth, nor is it levitating off the surface of the Earth. So the acceleration in y is 0. And we can solve for the weight of the cart using W equals mg. It works out to 981 newtons. We put this information into the force balance. Step 7. We solve for the normal force. A little algebra and we get 981 newtons. That accounts for the forces in y. What about the forces in x? Well, let's return to step 4. The total force in the x direction consists of two tensions, T1 plus T2. We add them since they are pointed in the same direction. Step 5. We apply F equals ma. That gives us T1 plus T2 equals mass times acceleration in the x direction. Step 6. Substitute everything that is known, the mass and the acceleration. Finally, step 7. Solve. The sum of the tensions is 100 I hat newtons. We were told the tensions are equal, so each individual tension is 50 I hat newtons. So the normal force is 981 newtons, and each tension is 50 newtons. We have now solved a puzzle where there were forces in both x and y, and two of them pointed in the same direction. In this video, we illustrated basic examples of solving puzzles with Newton's second law. In the next videos, we will look at more complex puzzles.